for the invitation. It's great to be back. I first walked these halls 45 years ago as a freshman. Well, not this hall, but the previous incarnation of this building. Okay, I want to talk about the continuum hypothesis. I'm going to start slow. So I want to introduce you to the ordinals. These are the transfinite numbers. Everything's a set for me. So simplest set is the empty set. That's the ordinal 0. The ordinal 1 is the set whose only member is the empty set. You take these two, you get the ordinal 2. In general, if alpha is an ordinal, alpha is just a set of all ordinals which are smaller than it. You can see that from the example. To get the next ordinal, alpha plus 1, you just add alpha to the set. Omega denotes the least infinite ordinal, and it's the set of all finite ordinals. So using the ordinals in a transfinite induction, you can present the universe of sets. What you do is you transfinitely iterate a simple operation, the power set operation. So given a set X, P of X denotes the collection of all subsets of X. And then you can form the cumulative hierarchy of sets. So you start with nothing. At a successor step, you take the power set. And at a limit stage, you just take the union. And it's not hard to show that this is an increasing sequence. If X is a set, then X belongs to V alpha for some alpha. That's a consequence of the basic axiom. The other way you could do it, you could define this as the conception of sets, this construction, and then you could back out the axioms. Either way is fine. Okay, so let's look at these. We want to understand all mathematical questions are questions about the universe of sets. It's nicely layered for us. So why don't we just look at it level by level? Maybe it's not so hard. So V0 is pretty simple. That's the empty set. V1, that's got to be the power set of V0. And then V2's got to be the power set of V1. Well, look, those are just the first 3 ordinals. V3 has 4 elements, not an ordinal. V4 has 16 elements, so far not so bad. V5 has 65,536 elements, so it's gotten a little bigger. And then V1000 has a lot. V omega is infinite. If we just jump up to the first infinite ordinal, and it's a set of all hereditarily finite sets. The structure of V omega, that set with its membership relation, is mathematically identical to number theory. Each structure can be interpreted in the other. Now, as a set theorist, I think this is a more natural structure, but probably everyone here will disagree with me on that. All right, so it's going beyond omega that takes you from number theory into set theory. So I want to introduce you to cardinals, concepts that are equivalent in the finite split in the infinite. An ordinal, which is rigorously defined, is a cardinal if every smaller ordinal has smaller cardinality. So you can't find a bijection between alpha and any smaller ordinal. The finite ordinals are all cardinals. Omega is a cardinal. For each ordinal alpha, omega alpha denotes the alpha infinite cardinal. So omega 0 is omega formally, but we never use that notation. Omega 1 denotes the least uncountable cardinal. Omega alpha plus 1 is the least cardinal bigger than omega alpha. By the basic axioms of set theory, for every ordinal alpha, omega alpha exists. So there are lots of cardinals. There are as many cardinals as there are ordinals. It also follows from the axioms of set theory that if you have an infinite set, then its cardinality is measured by a cardinal. So there is an alpha such that the cardinality of x is omega alpha. That requires the axiom of choice. All right, so now we come to the continuum hypothesis. It starts with the theorem of Cantor. If you let n be the set of natural numbers and r the set of real numbers, they do not have the same cardinality. Different sizes of infinity. Assuming the axiom of choice, the cardinality of the reals is omega alpha for some alpha. Which alpha? The continuum hypothesis is the assertion that if you have an infinite set of real numbers, then either it has the same cardinality as the natural numbers, or it has the same cardinality as the real numbers. So, assuming the axiom of choice, the continuum hypothesis is equivalent to the assertion that the cardinality of the reals is omega 1. Now, yesterday, we were told there are only two kinds of equations in that. Well, that's an equation. It doesn't look like a differential equation. So, well, maybe. So maybe there's a third kind. But enter the house of set theory at your own peril. This question has driven many people crazy. The continuum hypothesis in mathematics, this is Wikipedia scholarship. I'm sure it's all correct. In 1900, at the Second International Mathematical Congress in Paris, Hilbert posed his now famous list of 23 questions to guide mathematics for the coming century. The problem of the continuum hypothesis was the first problem on the list. In 1904, at the Third International Mathematical Congress in Heidelberg, Koenig gave a lecture in which he claimed to solve CH. All the parallel sessions of the Congress were canceled so that everyone could attend Koenig's lecture. The announcement was a sensation and widely reported in the press. The Grand Duke Frederick I of Prussia had Felix Klein explain the entire matter to him personally, but the proof was wrong. So I'm not quite sure how that played out. Many others tried to solve the problem of the continuum hypothesis and failed. Hilbert apparently thought he had a proof for 2 years. The problem of the continuum hypothesis quickly came to be widely regarded as one of the most important problems in all of modern mathematics. In 1940, Gödel showed that it's consistent with the axioms of set theory that the continuum hypothesis be true. So you can't refute the continuum hypothesis. And then the modern era of set theory arguably began in 1963 with Cohen's announcement at Berkeley on July 4th that it's consistent with the axioms of set theory that the continuum hypothesis be false. So you can't prove the continuum hypothesis. The fact that July 4th is Independence Day, I'm sure is a coincidence. What we say, or what these two results tell you, is that the continuum hypothesis is independent of the axioms of set theory. Now, I want to say a little bit about Cohen's method, nothing terribly technical. The ZFC axioms, those are the axioms you would back out from that cumulative representation of the universe of sets, just as you would back out the piano axioms from the standard conception of arithmetic. These axioms formally specify, let's call them the founding principles for the conception of the universe of sets. But you might be studying the universe of sets, but you can look at toy universes or models. If M is a model of set theories, that's just an algebraic object, then what Cohen showed is that M contains blueprints for virtual models of ZFC which enlarge M. And these blueprints can be constructed and analyzed within the initial model. If M is countable, then every blueprint constructed within M can be realized as a genuine enlargement of M. Cohen proved that every model of ZFC contains a blueprint for an enlargement in which the continuum hypothesis is false. So if there is a model of ZFC, then there's one in which the continuum hypothesis is false. You just pass to a countable model. Cohen's method also shows, but that was a slightly later discovery, that every model of ZFC contains a blueprint for an enlargement in which the continuum hypothesis is true. So what Cohen really solved was the extension problem. Gödel, and I'll say more about what Gödel did later, solved the submodel problem. Just what you have to keep in mind is a model of ZFC is an incredibly complicated object. So complicated that you can't prove it exists. But what Cohen did, this is a leverage game. You can't prove the model exists, but if you've got a model, you can use it to build other models. Okay, what about Cohen's method? It's much more chaotic than just CH. The method has been vastly developed in the 5 decades now since Cohen's original work. Many problems have been shown to be unsolvable, including problems outside set theory. There was a Whitehead problem, group theory, Kaplansky's conjecture, Susslin's problem, Borel conjecture, and it's still happening. More recently, the Brown-Douglas-Fillmore automorphism problem. So it doesn't happen a lot that problems that arise outside of set theory are shown to be unsolvable, but all of these did. Okay, maybe it's time to give up. You know, maybe it just was a good attempt at set theory. Maybe the ubiquity of unsolvable problems is an indication that it's an incoherent conception. We got misled. Well, large cardinal axioms, which are axioms that assert the existence of very large sets, are not provable by Gödel's second incompleteness theorem. The large cardinal axioms are falsifiable. Might lead to a contradiction. So I'll make my standard prediction. No contradiction in the existence of infinitely many Woodin cardinals will be discovered in the next 1,000 years. Not by any means whatsoever. I don't care if we encounter an extraterrestrial civilization that's been doing mathematics for 1 billion years. Okay, that's a pretty precise prediction. It's a prediction about our universe, next 1,000 years. 1,000 years, we'll know whether I'm right or not. Now, the real claim, of course, is that there's no contradiction from the existence of infinitely many Woodin cardinals. Now, these statements cannot be formally proved. They can only be refuted. This suggests there's a component in the evolution of our understanding of mathematics which is not formal. There's mathematical knowledge which is not entirely based on proofs. So the skeptic is in a, say you are comfortable with arithmetic truth. So you have to regard any statement about the numbers as either true or false. The claim that the existence of Woodin cardinals does not lead to a contradiction is an arithmetic statement. Now you can say it's not interesting, but you have to say that it's either true or false. No one has come up with a method for arguing that large cardinals don't lead to a contradiction, except for the conception of the universe of sets in which those large cardinals exist. There doesn't seem to be any other way. Okay, so now we can get trapped by the skeptic. All right, I buy that. You have this conception of the universe of sets is populated, well, I guess you like Woodin cardinals, they're populated with Woodin cardinals, whatever. Tell me whether CH is true or not. How can you have a conception of the universe of sets and declare it as meaningful and talk about the existence of really big sets if you can't answer the most basic question about small sets? So now the tables have turned, and we have to investigate CH. Well, in mathematics, if you've got a complicated problem and you're trying to figure out the answer, why don't you look at special cases? But how do you look at special cases for the continuum hypothesis? You're not going to run off calculations. Well, you can look at simpler sets. So I'm going to talk about, I'll call them the simplest uncountable sets. Now this is not an entirely standard definition, but it's equivalent to a standard definition. First of all, let's look at v omega plus 1. That's the first stage in the cumulative hierarchy, which is uncountable. That's the Cantor set in disguise. Well, we'll call a subset of that to be a projective set if it can be logically defined in the structure of v omega plus 1 epsilon. We're really talking about second order number theory. But we also want to talk about relations, so we'll just make the same definition. A binary relation on v omega plus 1 is a projective set if it can be defined as a binary relation in the structure of v omega plus 1 epsilon. Okay, so let's now state the continuum hypothesis. Let's not talk about reals. Let's talk about v omega plus 1. So the continuum hypothesis is equivalent to this statement. It says that if you have a subset of v omega plus 1, think the reals, then either A and v omega have the same cardinality, v omega is really n, or A and v omega plus 1 have the same cardinality. But we're shifting to v omega plus 1 because we have a natural notion of a simple set. Well, we've defined the simple set so we can projectify this statement. And that's the projective continuum hypothesis. If A, subset of v omega plus 1, is an infinite projective set, then either A and v omega have the same cardinality, or there's a bijection that has a binary relation, which is a projective set. Now you might say, why don't I have projective here? Well, all the countable binary relations are projective. So if you have a bijection between A and v omega, that's a countable binary relation in v omega plus 1. It's projective. So no need to isolate that. So all we're doing is taking the continuum hypothesis, which is a statement about all sets, and we're localizing it to simpler sets. Now we can do the same thing with the axiom of choice, because that was another issue that Hilbert raised. So first I have to tell you what the axiom of choice is. If you have a subset of x cross y, arbitrary sets, a function is a choice function for that set. If for all points in A, if there is a point B which when paired with A is in the set A, then f picks such a point. So it's just this. You got x. These are not drawn to scale. This is A. And that's the function. Okay, but we can projectify this. So in the axiom of choice is the assertion that for every subset of x cross y, there's a choice function. Well, we now can projectify this. And we can define the projective axiom of choice. If A is a subset of v omega plus 1 cross v omega plus 1 is a projective set, then there's a function which is a choice function for A and which is a projective set. So in each case, the projective CH, continuum hypothesis, or axiom of choice, we just replace set by simple set and we get statements. So why don't we investigate these? They did. These were investigated in a slightly different guise in the early 1900s. They're both unsolvable. In fact, in an amusing coincidence, if you look at the actual constructions of Gödel and Cohen that showed that the continuum hypothesis was unsolvable, shows these are. In Gödel's universe L, that's how he showed that the continuum hypothesis was consistent. The projective axiom of choice holds and the projective continuum hypothesis holds. So you're not going to refute either of these from the ZFC axiom. In the actual enlargement of L provided by the blueprint which Cohen defined for the failure of CH, the projective axiom of choice is false, as is the projective continuum hypothesis. It doesn't look like we've made much progress. We decided to look at some special cases, and they're unsolvable. but the intuition that they have answers is correct. It took a long time to get to that point, but that happened. So if you go beyond the basic ZFC axioms, you have the large cardinal axioms that assert the existence of very large sets. Okay, such axioms assert the existence of large cardinals. So I'll give you some samples. Measurable cardinals, Woodin cardinals, and then a whole bunch. Names aren't so exciting. The strength increases as you go down. This is not the historical order. These were discovered, and these, then these were discovered, and these are much smaller, and this was discovered. Now, you wouldn't think that large cardinals would have much influence on small sets. Like take the projective sets. Why would the existence of some enormous infinite set tell you something about the projective sets? Remarkably, it does. So if you have infinitely many Woodin cardinals, then the projective continuum hypothesis holds. And then, rephrasing a more significant theorem, Martin and Steele showed about a year later, if there are infinitely many Woodin cardinals, then the projective axiom of choice holds. So both those problems, remember, were unsolvable, but you bring in infinity and you get the answers. So this is looking now promising again. In fact, I would argue we now have the correct conception of V omega plus 1 in the projective sets. This conception yields axioms for the projective sets. These determinists, the axioms, are in turn closely related to and follow from large cardinal axioms. So what really happened is you have the piano axioms for arithmetic. V omega plus 1 is really second order number theory, and we now have the analog of the piano axioms for second order number theory, and it gives a rich, robust theory. Well, this looks good. We did the special case, so let's go on. So I have to introduce you to the definable power set. If X is a set, P def of X denotes the set of all subsets of X, such that the set Y could be logically defined in the structure X epsilon from parameters. So we don't necessarily take all the sets, we take those which are somehow intrinsic to the set X itself. The collection of the projective subsets of V omega plus 1 is exactly the definable power set. But wait a minute. We have a conception of the universe of sets as iterating the power set operation. What if we replace the power set operation by the definable power set? And that's exactly what Gödel did. So let me remind you about the cumulative hierarchy of sets. Remember, we start with nothing. We iterate at a successor step. We take the power set. At a limit stage, we take the union. And V is the class of all sets that you catch this way. So we're just going to replace the power set by the definable power set. This gives you Gödel's universe L, which I've already mentioned. You start the same way, but now at a successor step, you take the definable power set instead of the full power set. At limit stages, you take the union, and then L is the class of all sets X, such that X belongs to V alpha for some alpha. Okay, now this is a much more slowly growing hierarchy. In general, L alpha is not V alpha. Okay, but this suggests an axiom. The axioms of set theory tell us for every set X, there's an alpha for which it belongs to V alpha. Why don't we just formulate that axiom, but use this hierarchy instead? And that's what Gödel did. The axiom V equals L. Suppose X is a set, then X belongs to L. So there is an alpha such that X belongs to L alpha. So iterating the definable power set gets all sets. And Gödel showed that if you assume V equals L, then the continuum hypothesis holds. Now jumping forward to Cohen's forcing, if you have a Cohen blueprint for V equals L, then the axiom V equals L must already hold and the blueprint is true. adopting the axiom B equals L completely negates the ramifications of Cohen's method. This looks great. There's a problem, obviously. Scott, before Cohen's work, showed that if you assume this axiom B equals L, there are no measurable cardinals. There are no large cardinals. There are no Woodin cardinals. Well, that's a little disturbing to me. So the axiom B equals L is false. So it was like a bait and switch. We got a great axiom, B equals L. It's immune to Cohen's method, but the universe of sets is supposed to have everything in it. It's supposed to be transcendent. And so the very principles we use to generate richness in the hierarchy of sets tells us we have to reject this axiom. So what are we going to do? Well, somehow the projective sets led us to the axiom B equals L and the construction, rewriting history. Maybe we can, if we generalize the projective sets, we can find the ultimate version of L. Or maybe the ultimate version of the axiom B is L. So the trouble with the construction of L is you're iterating the definable power set. Maybe it should be a richer operation, and maybe the large cardinals give us an enhanced definable power set. And we should really be iterating the enhanced definable power set. Well, but then what's an enhanced definable power set? That all starts to look murky and very complicated. So let's try to do an end run around it. So I'm going to talk about the universally bare sets. Now, the projective sets are built from below. You just define B omega plus 1 and you extract the projective sets. We really want to get at a generalization of the projective sets that's not from below in any sense. It should couple into the universe of sets if it has any chance of giving us or leading us to the correct generalization of B equals L. Okay, so I'm going to work in Euclidean space, doesn't really matter. If you take a subset of Rn, it's universally bare. If its continuous pre-images in any topological space have the property of bare, differ from an open set by an eager set in that space. So as you vary the space omega, this is either trivial or non-trivial. If omega is a discrete space, well, it's pretty trivial. If omega is Rn, and you take pi to be the identity, you see that A has to have the property of bare. And if you replace omega by the stone space of a measure algebra, you can get Lebesgue measurability. So this is kind of a universal nice property. Universally bare sets are Lebesgue measurable, they have the property of bare, they have all the classical regularity properties. Seem quite interesting. Now if you assume D equals L, something very strange happens. Every set of reals is the image of a universally bare set by continuous function. So the universally bare sets are not closed under continuous images, but the projective sets are. Well, that suggests maybe this isn't the right notion. Or maybe it suggests we need to bring in large cardinals to clarify the picture. So you can relativize the construction of L to any set, and particularly you can relativize it to a set of reals. All you do is you start, instead of with the empty set, you throw the reals and the set of reals in at the bottom, then you just iterate the definable power set. And then L of A and R, that's L relativized to A and R, is a class of all sets you can generate this way. And we're going to be interested in the sets of reals there. They're in some sense all the sets of reals that must exist from the axioms of set theory without the axiom of choice, given that A exists. Very complicated sets of reals. Okay, and these are, in the right context, the ultimate generalization of the projective sets. So if you assume there's a proper class of Woodin cardinals, Barth and Steele showed that if A is universally bare, then A is determined, just like with the projective sets. Steele showed that if you have a universally bare subset of R cross R, It has a choice function, which is universally bare. I showed that if you have a proper class of Woodin cardinals and A is universally bare, then all the sets you can generate from A by relativizing Gödel's construction are universally bare. So in particular, they're closed under continuous images. And in fact, L of A and R models AD, where AD is the axiom of determinacy. So in the context of a proper class of Woodin cardinal, the universally bare sets are a very rich collection. And they have tremendous structure. So I want to talk about measuring the complexity of the universally bare sets to motivate how we're going to use them. So I'm now changing a standard definition slightly just to make things a little easier. If A and B are subsets of a Euclidean line, we'll say A is weakly wage reducible to B if there's a continuous function on the irrationals such that either A is the preimage of B or it's the complement of the preimage of B. So the idea here is that if you know A, if you know B, modulo that function, which has only a countable amount of information in it, because it's continuous on the irrationals, you can compute A. So from B, you can compute A. It's a complexity notion. We'll say that A and B are weakly bi-reducible if each is weakly wage reducible to the other. This is an equivalence relation, and so we can take the equivalence classes. Well, it doesn't seem like a terribly useful notion until you localize it to the universally bare sets. Assume there's a proper, this is combining many theorems, assume there's a proper class of Woodin cardinals, then the weak wage degrees of the universally bare sets are linearly ordered by weak wage reducibility. And this linear orders are well ordered. So all these very complicated sets are laid out for you in a hierarchy that's well ordered. And this is a very fine hierarchy. The Paracels sets don't even occupy the first omega 1 levels. Okay, so that suggests that we might be able to use the universally bare sets to get the ultimate generalization of the axiom V equals L. We wanted some kind of enhanced power set. We've got rich structure here. How are we going to use it? Okay, I have to make some elementary definitions. Set M is a transitive set if every element of M is a subset of M. Each V alpha is a transitive set. If M is a finite transitive set, it's in V omega. And V omega is just a union of all finite transitive sets. A transitive set is like an initial segment. A member of a member is a member. That's why transitive. A sentence is a sigma 2 sentence if it can be written as in the following form. There is an ordinal alpha such that a V alpha satisfies psi for some set in psi. Something happens in a V alpha. It's an incredibly powerful, sigma 2 can say a lot. All questions of mathematics classically discovered are sigma 2, classically looked at as sigma 2 sentences. Okay, so when we want to define V as ultimate L without defining L, how about we define V as L without defining L? So for each n alpha, we could intersect all the transitive sets, now this may be empty, M, such that n models ZFC minus power set. Now ZFC minus power set are the ZFC axioms where you throw out the power set axiom, keeping infinity. You can still prove that every infinite set has a cardinality. We want alpha to be contained in M, and we want the ordinals of M to be alpha. So that's n alpha. We just intersect them all. There may be none. Now the following are equivalent. The axiom of V equals L, which I've already defined, for each sigma 2 sentence phi, if phi holds to V, then there's a countable ordinal alpha such that n alpha satisfies phi. So all you have to do is, these are the test models. And if you can reflect every true sigma 2 sentence into a test model, that's equivalent to V is equal to L. All right, so that will be the template for trying to generalize V equals L, but we need test models. Okay. Well, we're going to start with HOD. This is another important definition of Gödel, HOD, H-O-D, that's hereditarily ordinal definable. It's the class of all sets X such that there exists an ordinal alpha, and M is V alpha, X belongs to M, and M is transitive. Every element of M is definable in V alpha from ordinal parameters. HOD is the class of all sets. This is a meta-lemma because it's not first order. It's a class of all sets that there exists a transitive set M such that X is in M, and every element of M is definable in V from ordinal parameters. That's why it's hereditarily ordinal. Now you can work this definition of HOD in models where the axiom of choice fails. No use of the axiom of choice. Gödel did that to give another proof of the consistency of the axiom of choice for the axioms of set theory, or at least that was, I think, his intent. So in particular, we can work or define HOD L of R within L of A and R, where A is a set of reals, possibly a universally bare set. So the notation is if A is a set of reals, HOD super L of AR is the class HOD as defined within that universe. The axiom of choice always holds when you compute HOD, and so that will be true even if L of A and R is a model of the axiom of determinacy, which denies the axiom of choice. And the first connection between determinacy and large cardinals was this theorem of Solovay, over 50 years ago now. Assume you have a set of reals and the axiom of determinacy holds in L of A and R, then the omega 1 of V, which is a measurable cardinal in the HOD of L of A and R. HOD of L of A, this is not going to have all the reals, so there's no reason to expect that this is the omega 1 of this model, and it's not. It's a large cardinal. Well, this is looking promising. There's a slight problem. Suppose there's a proper class of Woodin cardinals and that A is universally bare, then omega 1 of V is the least measurable cardinal of HOD. There's not enough richness in the HOD of L of R, L of A and R below omega 1. So our test models can't be countable. We can't just cut HOD at omega 1. So we need to look elsewhere. Well, a natural ordinal that comes up is theta of L of A and R. That's a supremum of the ordinals, such that there's a surjection of the reals onto alpha such that pi is in L of A and R. This is a kind of measure of the size of the continuum from the point of view of L of A and R. And it really is very much like omega 1. Omega 1 is a supremum of the ordinals onto which you can map omega. So we're just moving from surjective images of omega to surjective images of the reals, or the power set of omega. Well, something interesting happened. Suppose you have a proper class of Woodin cardinals. A is universally bare, and kappa is greater than or equal to the theta of L of A and R. Then kappa is now measurable. So below omega 1 and above theta, nothing's happening. All the excitement, if there is any excitement, has to be between omega 1 and theta. But there's some indication that there's plenty of excitement, because if you have a proper class of Woodin cardinals and A is universally bare, then the theta of L of A and R is a Woodin cardinal in the HOD of L of A and R. So that ceiling in the large cardinal is actually a Woodin cardinal. And this is a symptom of a deep structural relationship between large cardinals and determinacy. Well, now we're all set to state the axiom V is ultimate L. The existence of a Woodin cardinal, and I'm not going to define it, is expressible by a sigma 2 sentence. Woodin cardinals exist in V. If A is universally bare and there's a proper class of Woodin cardinals, then the HOD of L of A and R thinks there is a Woodin cardinal. So we've reflected a sigma 2 sentence true in V into the HOD of L of A and R. So that suggests our axiom. The axiom asserts there's a proper class of Woodin cardinals. That's to make the universally bare sets behave properly. And then just for every sigma 2 sentence phi, if phi holds in V, then there's a universally bare set A such that the HOD of L of A and R satisfies phi. These are our test models. And because of the weak wage reducibility hierarchy, if A is less complicated than B, you fact, the HOD of L of A and R is computed inside the HOD of L of B and R. So these really, in some sense, fit together. So that's the axiom, or the candidate axiom. Now, because it's stated this way, and because these sets are all models of AD, we can now couple into the enormous theory that's been developed in descriptive set theory in the context of AD. Much of that took place here at Caltech and at UCLA. So you can prove you can actually prove things from this axiom. So you can prove the continuum hypothesis. You can prove V is equal to HOD. So suppose there's a Cohen blueprint for V is ultimate L, then the axiom V is ultimate L must hold in the blueprint is trivial, just like L. Adopting the axiom V is ultimate L completely negates the ramifications of Cohen's method, just like V equals L does. But we have an issue. And the issue is we rejected V equals L because there was a large cardinal that denied it. So we have that same problem. Okay, so we need to look at that. So I need to tell you a little bit about the language of large cardinals, how they're formulated now. If you have two transitive sets, a function from one to the other is an elementary embedding if it preserves truth. So whenever you choose points in X in a formula, if X thinks that formula holds at those points, that holds if and only if Y thinks that same proposition holds about the image points. The embedding preserves truth. Now, isomorphisms are clearly elementary embeddings, but there are no non-trivial isomorphisms between transitive sets. All right, so I'm not going to define, in fact, I'm going to define one large cardinal. That was on my list, extendable cardinals. It's nicely phrased as elementary embeddings. So, first of all, I'll show you something. Suppose that you have an elementary embedding from V alpha to V beta, then the following are equivalent. It's not the identity, and that's one. And two, it's not the identity on the ordinals. So a non-trivial elementary embedding from V alpha to V beta has to move an ordinal. The critical point of J denotes the least ordinal. Remember, the ordinals are well ordered. So if J is not the identity, there has to be a least ordinal that J doesn't send to itself. J has to be increasing. And then that leads you to the definition of an extendable cardinal, which is in Reinhardt's thesis. Delta is an extendable cardinal if for every lambda, it's bigger than delta, there's an elementary embedding from V lambda plus 1 to Vj of lambda plus 1 with critical point delta and J of delta bigger than lambda. It's pushing up. Okay, so a few more definitions, I apologize. Transitive sets H gamma, for every infinite cardinal gamma, H gamma denotes the union of all the transitive sets M of cardinality less than gamma. So H omega is V omega, H omega 1 and V omega plus 1 are logically equivalent structures, just as V omega plus 1 number theory are. H omega 1 satisfies all of the axioms of set theory except power set. For any infinite cardinal gamma, remember gamma plus was the least cardinal bigger, H gamma plus will satisfy ZFC minus power set. So this is another way of stratifying the universe of sets besides the V alphas. Now, a transitive class, we want to talk about transitive classes, but how do you talk about classes when we're supposed to be talking about sets? We talk about definable classes. Just like you talk about a set of prime numbers in number theory, even though that set is not a number. So a transitive class is an inner model if it contains all the ordinals and all of the axioms of ZFC hold in that class, when interpreted in that class. Now that's not first order. But there's a nice equivalence, a surrogate definition, which is first order. And that is, M is suppose it's a transitive class containing the ordinals, and I'm thinking of a definable class. Then the following are equivalent. M is an inner model, so this is happening. And second, for every infinite cardinal gamma, M intersect H gamma plus satisfies ZFC minus power set. And the point is that this is a first order condition. That's a legal statement. So if I have a definable class, it's legal to check that. If that holds, I say that holds. L and HOD are inner models. Okay, so but we're trying to get at V is ultimate L doesn't deny large cardinals. We need some measure that an inner model is close to the parent universe. Now, there are many routes toward this, and actually many independent routes were taken, but a particularly elegant one was through the Hampkins. Suppose N is an inner model. Remember, it's an inner model GFC, and delta is an uncountable regular cardinal, like omega or omega 1. Well, omega 1, that's said uncountable. N has a delta cover property if every subset of N of size less than delta can be covered by a set in N of size less than delta. Small sets can be covered by small sets. Now, this would be trivial if delta was omega. We don't use this in the case of omega. N has a delta approximation property if for all sets X, the following are equivalent, it belongs to N, and all of its small pieces belong to N. So if you have an arbitrary subset of N, and its intersection with every set in N of size less than delta is in N, it must be in N. Now, if I used omega here, there's only one inner model that can satisfy it, and that's B. Okay, so that's why we don't use omega. Okay, so Hampkins proved a remarkable theorem. If N and N0 and N1 both have the delta approximation property and the delta cover property, suppose they do, suppose their intersections with H delta plus are the same, then they are the same. So inner models with a delta plus cover and approximation property are necessarily definable inner models from a parameter. Okay, but then, so that's the uniqueness theorem, and then Hampkins also proved the universality theorem, which I'm only stating for extendable cardinals. That's the only large cardinal I've defined. Suppose N is an inner model with a delta cover and approximation property. Kappa is bigger than delta, and kappa is an extendable cardinal. And kappa is an extendable cardinal in N. Now, this fails to generalize to the axiom I0, and we want to get at all large cardinals. So we need a third property, and that's the DeltaGenerousity property. Suppose N is an inner model, sigma is a subset of N, then N bracket sigma is the smallest inner model such that M, such that N is included in M and sigma belongs to M. It always exists. Suppose N is an inner model and delta is strongly inaccessible. That means 2 to the kappa is less than delta for all kappa less than delta, and it's regular. Then N has a DeltaGenerousity property if for all small subsets of delta, N bracket sigma intersect V delta, that's a ZFC model, is a Cohen extension of N intersect V delta. So we're just bringing in another property. And the reason to bring this in is we get the full universality theorem. If N has a delta approximation, delta cover, and the DeltaGenerousity property, suppose the axiom I0, and this is just a sample, holds at lambda for a proper class of lambda, then in N the axiom I0 holds at lambda for a proper class of lambda. All large cardinals go down. Okay. Now there's an obvious conjecture. The ultimate L conjecture. Suppose delta is an extendable cardinal, then provably there's an inner model N such that N has the 3 properties, delta cover, delta approximation, and DeltaGenerousity, and N satisfies V as ultimate L. Now, by the universality theorems, if you can prove this theorem, V as ultimate L is compatible with all large cardinals. Now, right, by the universality theorems. There's no Scott's theorem. Now, I want to stress that the ultimate L conjecture is an existential number theoretic statement. It's saying provably, if it's undecidable, it's false. Right? An existential statement about numbers, which is undecidable, is false. If it were true, you'd verify. So, the ultimate L conjecture must be either true or false. Unlike CH, you cannot argue that it's meaningless. You're arguing that an existential statement about the integers is meaningless. I'm not saying that this is an interesting number theoretic statement. I'm just saying you can't say it's meaningless. All right, so we're now in an interesting situation. I would say set theory faces one of two futures. The ultimate L conjecture, first of all, this is now my claim, I'll be controversial, but the ultimate L conjecture reduces the entire post-Cohen debate on set theory, on set theoretic truth, to a single question which has to have an answer. It's an existential number theoretic statement. Future one. The ultimate L conjecture is true. Then the axiom V is ultimate L is very likely the key missing axiom for V. There's no generalization of Scott's theorem for the axiom by the universality theorems. All questions which have been shown to be unsolvable by Cohen's method to date are resolved modulo large cardinal axiom. So V equals ultimate L, like V is ultimate L. The reason it negates Cohen's method is you can think of the universe of sets as having two dimensions. It has a width and it has a height. The height is a large cardinal issue. The width is how many reals do you have? How many sets of reals? V is ultimate L, as does V equals L, binds the height to the width. If you change the width, you can't recover the axiom without changing the height. And what Cohen's method does is it changes the width and preserves the height. So that's why it's useless. It cannot affect the axiom. So that's future one. Future two is the ultimate L conjecture is false. Well, then the whole program to understanding V by generalizing the success we had in understanding V omega plus 1 in the projective sets fails. It's back to square one. So, which is it? Now, I realize I have to show a picture. And to me, I really think the set theory is at a critical crossroads. And we have to resolve this conjecture, and the future will be very different. I happen to think that in this future, obviously I'm a little biased, the set theory will really start to get off the ground. The trouble with set theory now is you work from the ZFC axioms, almost everything is independent. How do you build a rich structure theory if everything's independent? It would be like walking up to a cathedral that you want to investigate, and there's a doorkeeper. And the doorkeeper says, well, you say, well, where's the door? And the gatekeeper says, well, where would you like it? Then you enter the door and say, well, what's over there? What would you like to be over there? There's no structure. Set theory with forcing is a study of the landscape of possibilities. It's not the study of what is. And so you can't develop a rich structure theory in that setting unless you can somehow eliminate forcing. So that's just my view on it. If this happens, boy, it's really back to square one. So at set theory, I think we are either going to face a bright future or a dark future. Now, a bright future is like the sun rising, and the dark future is like the sun setting. So that's my picture. All right, now this is Caltech. You might look at that picture and say, yeah, that's a nice sunrise or sunset picture, depending on the future. This is not Earth. It's Mars. And this is from the lander. And so this is what the sunrise or sunset, I didn't actually look at which it was, appeared to the lander. The clue, of course, is the sun seemed a little bit smaller than it should be. But other than that. So that's where we are. I think it's an exciting time in the subject. And hopefully, before too long, we'll know the answer. So thank you.
So, any question? this is from a non-expert. If the ultimate L conjecture is false, that doesn't preclude the fact that there could be another conjecture.
Yeah, there could be, but if the ultimate L conjecture is false, it depends how it's false, but it's saying that the whole program of how we build enlargements of L fails. So the whole program we use.
Any sort of enlargement, or just?
So the way things work now is you build L, Scott comes along and says there's no measurable cardinals. Then you can enhance the definable power set and build an enlargement of L with a measurable cardinal. Oh, but wait, then they're not two measurable cardinals. So there's a whole area of set theory that constructing ever more complicated enlargements. You can build the enlargement for one Woodin cardinal, but in that enlargement they're not two Woodin cardinals, and so forth. But all of these constructions share a similar feature, and it's hard to imagine a construction that doesn't. And what the ultimate L conjecture does is to really distill out that feature. So if the ultimate L conjecture is false, you're at a threshold in the large cardinal hierarchy which is beyond analysis according to the way that we currently do it. There's another issue which I didn't dwell on. The large I0, the large cardinal axioms go beyond I0. But then they enter a realm where the notion of large cardinal is so large, it denies the axiom of choice. Oh wait, I said the only way to verify the claim a large cardinal is consistent is to have it true in V. The strongest large cardinals we know of deny the axiom of choice. Does that mean we're denying the axiom of choice for big sets? And if you go down that road, not only is it dark, but it's foggy and you can't do anything. Because you give up the axiom of choice, everything falls apart. There's the issue in that if you take that view seriously, that the only way to authenticate a consistency claim is by an existence claim, and the only way to have the existences in this case is deny the axiom of choice, these axioms should be inconsistent. That follows from the ultimate L conjecture.
Could it be the countable choice is true, but not the full axiom of choice?
Yes, yeah. So these just say the axiom of choice fails way up high.
Right.
So down here where things are nice, you might have the axiom of choice, but once sets start getting too big, you get tired and you can't choose it. Yeah, that could happen. But more interestingly, the reason these axioms haven't been refuted is it's incredibly difficult to do a construction without the axiom of choice. The ultimate L conjecture, which is a ZFC conjecture, wipes them all out. So something else will happen if one proves the ultimate L conjecture. It will be the first time that a large cardinal axiom, well motivated by large cardinal principles, has been shown to lead to a contradiction by a deep structural argument. All inconsistency proofs so far have been relatively easy. And that's kind of strange, right? Every theorem is an inconsistency result. And there are very deep theorems, even in set theory. But no one has proposed a large cardinal axiom which leads to a contradiction by deep structural argument. It just hasn't happened yet. So that in the future one, there'll be a whole wave of such results.
Maybe I missed this, but what does the V equals ultimate L say about the continuum hypothesis?
It implies the continuum
Yes.
hypothesis. And it implies, curiously, we don't yet know it implies GCH, the generalized continuum hypothesis. And that's because V's ultimate L is an end run. We don't know how to build the model yet. Once we know how to build the model, we'll have all the tools to analyze it. The idea was just to come up to try to guess what the axiom is, maybe prematurely, before knowing how to build the model. And the reason to do that is to open the door for an anti-theorem. In other words, you don't want to spend all your time developing a theory. You want to allocate some resources to showing that it cannot be developed. So in the abstraction of the ultimate L conjecture, it's a level playing field. Each side has a chance. right? You could work and try to prove it, or you could work and try to just prove a Scott's theorem. Okay, so that's the situation. That's why I think this will come to a conclusion. Hopefully it won't be 12 volumes and however many journal pages, but I think there's enough additional evidence for that dichotomy. There are other theorems that suggest that the ultimate L conjecture is true. I'm not telling you the whole story, and but it's a hard problem. Or so far.
Some results that have some people have mentioned that the cardinality of the real numbers might be out of 3. So that would be inconsistent.
Yeah, well, okay. So the nice thing about an unsolvable problem is you can change your mind. So 20 years ago, I was advocating actually L of 2, and I had arguments for it. But you have to go with the evidence. And the trouble is, a lot of those arguments are, I would call them R-centric. The view is that numbers and the reals, that's all the action. And there are all these sets up there, but who cares about it? So why should your intuitions about V be determined by local intuitions? They're only capturing a small piece of V. You don't want to overgeneralize. So I would argue that those intuitions that suggest C is L of 2, they're misleading because they're based on a very local view of the universal sets, ignoring the global structure. We'll see. I mean, it's a lot of work has been done with that. But there are fairly, I think, good arguments there, against the C is L of 2.
Just how old is the conjecture?
4 years.
Oh, okay.
Well, it's refined. There was an earlier incarnation of the conjecture 8 years ago, but as one investigates, one realized it wasn't quite right. The issue is the ultimate L conjecture, as I stated it, is reflecting sigma 2 sentences. There was an idea that you should be able to reflect sigma 3 sentences, which is more complicated, provided you chose the right test model. And that seemed like a very solid intuition, and it was made for a more useful axiom. And then I showed that that's not right. You have to only reflect sigma 2. So, but this in this form, so it's 3 years old, 2 years old. And there's progress on it. I mean, there are partial results. It's not like nothing's happening. But it's accomplished so far.
Any other questions?
What's the feeling of how many years until it's finished?
Well, I can always, I mean, look, someone in this room could refute the ultimate L conjecture tomorrow. Now, I don't have to resign my job because if you show Woodin cardinals are inconsistent, well, I did say I would resign my job, but I was at Berkeley at the time. I'm not quite sure what the ethical choice would be. I guess I could resign my emeritus status. So I think we're going to know within a year whether the current methods can achieve it or not. They're just so, the dichotomy of possibilities is sharpened so much that I really think it's either going to work or there's going to be an anti-theorem. But every now and then, what you think is a minor loose end that has to be worked out blows up and becomes the key problem. We don't have enough understanding yet. What we know is we know that the construction of ultimate L has to be very much different than the current construction. And the question is whether you can lay that out and do it, and that's underway. We'll see.
So which future of set point do you believe personally?
Well, I think I kind of indicated that. I'm still going with future 1 because I don't see an alternative. The future 2 is so dark. I mean, it would really, I mean, it's a little bit like Here's the depressing thought. The projective sets in the correct incarnation of second order number theory, this is not the algebraic geometric projective set, but second order number theory, those questions were studied in the early 1900s. By 1925, they looked really hard and used and said we're never going to know the answers and stuff like that. We've now solved them. It took maybe 80, 90 years. But you look at the ingredients of that solution were things they hadn't even imagined. Well, what if we're in the same situation now? That figuring out CH is going to involve ingredients we haven't even imagined. So that's the pause. Like, how can we be so confident that we really are on the cusp of figuring this all out? When, you know, are we, you know, it would be kind of a nice period of history, or set period of history to live in. But there's no real basis. Maybe, you know, there's something, you know, it's going to be 1,000 years from now when they're dedicating the next building and so forth. You know, they'll talk about those foolish set theorists from 1,000 years ago. They just had no idea. That's possible, and that's. But right now, there are enough partial results, and there's a clear line. So I think there's a good shot at it. Check the archive next summer.
More questions?